This is the Advanced Photon Source at Argonne National Laboratory. Often called the APS, it is one of the most productive X-ray light sources in the world. Owned and operated by the U.S. Department of Energy Office of Science, the APS makes its ultra-bright X-rays available to more than 5,500 scientists from around the world each year, who conduct about 6,000 experiments with it, producing about 1,500 peer-reviewed papers per year. The reason the APS attracts so many researchers is that it provides unique capabilities that enable discoveries in many scientific fields. From next-generation energy storage for batteries and power grids to tougher materials for bridges and other critical infrastructure. From ensuring the performance and reliability of the nation's strategic deterrent to advancing technologies for aerospace. From clean and renewable energy technologies to treatments and vaccines to fight infectious diseases, the APS makes important, necessary innovations possible. It does this by harnessing high-energy X-rays created here in the electron storage ring that is at the heart of the APS. Before being injected into this ring, electrons are accelerated by high-voltage alternating electric fields to 99.99% of the speed of light, at an energy of 7 giga-electron volts. The storage ring, with a circumference of about 2/3 of a mile, is made up of more than 1,000 electromagnets. At each bend in the track, the electrons generate synchrotron radiation in the form of photons. Those photons are sent to 35 different sectors around the ring, each one equipped for different kinds of X-ray techniques. The APS has more than 60 beamlines, with experimental stations at each one. With so many beamlines, the APS is a versatile tool for scientific discovery. APS scientists use 3 different mechanisms, diffraction, imaging, and spectroscopy, to characterize the physical and chemical structure of materials. Researchers are able to use the high-energy X-rays generated at the APS to peer inside even thick samples and image the structures of those samples at resolutions as fine as 10 nanometers. Because they are non-destructive and highly penetrating, APS X-rays can study materials under a variety of extreme environments, including temperature changes, pressure changes, flow conditions, and applied mechanical stresses. And APS beamlines have the ability to capture these effects in real time, down to picoseconds or over days. This allows researchers to see the smallest defects, cracks, and voids form in materials under extreme conditions, enabling the development of stronger materials for uses such as submarines, space vehicles, and airplane engines. Movies can be made with very high time resolution to examine complex fluid flows in fuel injectors and turbine combustors. It also allows scientists to look inside batteries and measure the ions moving through them as they charge, and to track the slow decay that happens over time due to repeated charging. This data will help scientists build faster charging, longer-lasting batteries for the next generation of electric vehicles. The APS is fully equipped for several diffraction techniques, such as macromolecular crystallography, allowing scientists to determine the exact structures of the proteins and nucleic acids that make up viruses and living organisms. With the resources of supercomputers at the Argonne Leadership Computing Facility, research teams can capture 3-dimensional images of atomic structures, allowing them to determine whether drug candidates, antibodies, and other potential treatments inhibit those viruses effectively. Several widely used drug treatments and vaccines have been developed based on APS data. Several APS beamlines are dedicated to spectroscopy to characterize the makeup of samples under various conditions. Researchers use these beamlines to closely examine the chemical nature of samples collected from the environment and those related to the nuclear fuel cycle. The high energy and high brilliance of the X-ray beams produced by the APS uniquely enable it to provide this chemical information with nanometer-scale spatial resolution, even in 3 dimensions. The APS makes all of these techniques available to researchers from around the world, which is one reason it has been a destination facility for X-ray science for more than 25 years. As powerful as the APS is now, a massive upgrade of the storage ring is in progress, one that will increase the brightness of its X-ray beams by up to 500 times and improve the focusing ability of the beams. This upgrade will include a full replacement of the ring's components with new state-of-the-art magnets, vacuum systems, and technology. 9 new feature beamlines to take advantage of the increased brightness and focusing ability, and enhancements to existing beamlines. This will enable more precise imaging, significantly shorter measurement intervals, and increased sensitivities to trace elements, which will open the door to even more discovery and innovation. With support from the US Department of Energy and the thousands of scientists who use its capabilities, the APS will keep shining brightly for years to come.